Hello. Welcome to next lecture in the series. Stars are not static objects. They are dynamic systems that evolve over time. In this lecture, we will understand how stars change during their lifetimes, and how these changes are represented on the Hertzsprung-Russell diagram. Do stars change over time? The answer is yes. Stars are not permanent objects. Over millions or even billions of years, their physical properties continuously evolve. Their temperature changes, their luminosity changes, their size also changes. And because of these changes, stars do not stay at one point. They move across the HR diagram during their lifetimes. Where do stars come from? Stars are born inside giant clouds of gas and dust in space. These are called molecular clouds, also known as stellar nurseries. Under the influence of gravity, these clouds begin to collapse. This gravitational collapse is the first step in the birth of a star. As the gas cloud collapses further, important physical changes take place. The temperature increases. The pressure increases. At the center, a dense object begins to form. This is called a protostar. A protostar is a young star, but it has not yet started nuclear fusion. As the core temperature continues to rise, it eventually becomes high enough for nuclear fusion to begin. Hydrogen nuclei start combining to form helium. This process releases enormous energy. This marks a critical transition, the birth of a true star. When nuclear fusion becomes stable, the star enters the main sequence. At this stage, two forces are balanced: gravity pulling inward and pressure pushing outward. This equilibrium makes the star stable. In fact, this is the longest phase in a star's life. During the main sequence phase, hydrogen is continuously fused into helium. The star remains relatively stable. Its luminosity and temperature change only slowly. Most stars spend about 90% of their lifetime in this stage. This is why the main sequence is the most prominent region on the HR diagram. Eventually, the hydrogen in the core begins to run out. As hydrogen burning slows down, fusion starts occurring in surrounding layers. The core contracts, and the outer layers respond to this change. This marks the beginning of the end of the main sequence phase. As hydrogen in the core is depleted, the star can no longer maintain its previous equilibrium. The star expands and cools at the surface. On the HR diagram, it moves away from the main sequence. This transition leads the star into a new phase, the red giant stage. In the red giant phase, the core contracts and heats up further. Hydrogen fusion continues in a shell around the core. The outer layers expand dramatically, making the star much larger and more luminous. Eventually, conditions become suitable for helium fusion in the core. Now, an important question arises. Do all stars evolve in the same way? The answer is no. A star's mass determines its fate. Low-mass stars evolve into planetary nebulae and finally become white dwarfs. High-mass stars, on the other hand, end their lives in powerful supernova explosions and may form neutron stars or black holes. Thus, stellar mass is the key factor controlling stellar evolution. If we track the position of a star on the HR diagram over time, we obtain what is called an evolutionary track. Different stars follow different paths depending on their initial mass. These tracks help us understand how stars evolve from birth to death. The HR diagram is not just a classification tool, it is a map of stellar life. It shows how stars are born, how they evolve, and how they eventually die. From the main sequence to red giants, and finally to white dwarfs, neutron stars, or black holes. All evolutionary paths are encoded in this diagram. In essence, the HR diagram tells the complete story of stars.